Hello, Dr. Nishant. So within a couple of minutes, we can start the session. And by the time I would like to introduce him. So first of all, we have been a good friend and we have worked together in PhD. So I have seen him working a lot, and he is interesting, hardworking, as well as what I could say. So innovative. Innovative is the word which suits him well. So coming to his profile, he has completed his PhD recently from IIT Ropar last year, and a master's from PU Chandigarh. And right now he is working in a big team within the University of Linkoping with the with a pioneer in wireless communication, Eric Larson, and his expertise lies in optimization. Especially, he dealt with some problems related to NOMA, UAV, of course, and right now he is working on next generation communication system. Also, he is actively involved in dissemination and podcast activities. You can also follow his channels for some great and innovative ways uh, how to introduce and reflect the concept of communication. So there is an innovative way to learn how to use communication. So overall, this is going to be a fun loving session for you. So stay connected, and again welcome Dr. Nishant to start your session today. The stage is all yours, Nishant.
Okay, thank you, Dr. Rohit. Thank you for such a nice introduction. Am I audible to you?
Yeah.
Okay, sure. So I have connected from my tablet as well as from my PC because I want to this. I like the way of presenting with the pen, tablet in hand. So I will just share my screen.
Okay. Your screen is visible.
Is it visible? Okay,
yeah,
thank you.
Your screen is visible.
Okay. Thank you. I would like to welcome you all to this talk. And in this talk, my objective will be to explain you the essence of optimization. How do we solve the optimizations problems? And if you have optimization problem, how you want to prove that, whether you have a convex function or whether you have a convex constraints. Then there are different ways of proving this, whether you can prove it analytically or you can prove it numerically. And then we will look at some examples of solving the optimization problem, some very heuristic approach kind of examples. And at the last, we will see some examples using how to solve this optimization problem using MATLAB solver. And these examples are from my research papers. Okay. Okay, so first thing first, what is optimization? So optimization is an important stage of engineering design. So this is said by Todd R. Kelly. And this is a process of finding the most effective as well as the favorable value or condition given the set of constraints. So what is the best that we can achieve if we have certain set of constraints? That is defined by the optimization. And we can do several things. It could include maximizing the factors such as productivity, strength, either it is reliability, longevity, efficiency, and utilization. And in wireless communication, we usually talk about maximizing the capacity, maximizing the sum rate, minimizing the outage, or some other like maximizing the minimum of sum rate. So these are all kind of objectives that we look into the wireless communication. Then what is the structure of optimization problem? So optimization problem looks like this. So you have certain objective, f naught of x. F naught is a function that is a function of several variables x, and these x, they are the design variables. It could be a scalar value or it could be a vector. And it could be in wireless, it could be scheduling or assignment, how the users are scheduled to the base station, and how many number of resources that we can allocate to a particular user. And this is the objective function that we want to minimize. And this x is the design variable that we want to optimize. Then we have constraints, which restricts our problem. And we have several set of constraints. Either we can have inequality constraints, or we can have equality constraints. And then there are several analytical techniques to prove that whether this problem is a convex problem or this problem is a non-convex problem, or there is some other kind of problems. There are many kinds of problem in this optimization. I will go through it in the next slide. So how these constraints are imposing the solution. So let's say we have a function. Let's say this is f naught of x. We have a single variable x, and let's say we have defined a function like this. Now, if you do not have any constraint and you just want to minimize this f naught of x, so where is the minimum point? So this would be the minimum value, and we call it as global minimum solution, because there is no other value that minimizes the function. And this is, let's say this is x dash, x prime. So now if we restrict our x to take values only within this range, so basically we are imposing a constraint on x such that x should be greater than some lower bound value or less than some upper bound value. So this is the lower bound value and we have upper bound value. And now with this constraint, we only have to look for the objective within this area. So now here, where is the minimum? So if you look at this point, this is basically the minimum of the function. And now this minimum is different from what we already had, the global minimum solution. So this is the difference that we have when we have constraints, because we want to check our optimization problem or the objective value corresponding to the constraints that we have. Okay, then we have different variations of optimization problem. We can either maximize the objective, we can either minimize the objective, or we can have multiple objectives. Let's say we want to minimize this function and we want to maximize f1 of x. It could be another variation of optimization problem. Then we can also have max min objective or min max objective. So these kind of objectives, max min objective or min max objectives, they are basically deals with the fairness of the problem. So whenever you are interested in the network performance, then you take objectives like minimizing or maximizing. And whenever you are interested in from the user's perspective, then we talk about max min objective or min max objective. And then we have two kinds of solutions to the optimization problem. One is the global optimal solution and other one is the local optimal solution. So when you have a convex problem, then you can always reach to the global optimal solution. But it is not the case when you have non-convex problem. So for non-convex problem, it is very difficult to achieve global optimal solution. And then you have to propose some heuristic approaches or some other algorithms that returns you the local optimal solution. Okay, then let me give you an example of this optimization problem. Let's say we want to minimize this function f naught xy, and this f naught of xy is given by this plot shown in the top left corner. And you have two variables, x and y. So the easy way that you can do is you can plot a 3D plot of this function f naught xy. So now you have plotted the 3D plot. So from just looking at the plot, you can see that this is the maximum point and this is the minimum value. And also you can also compute the contour plots of this 3D plot. Contour plot is basically you have a 3D plot, you just take a parallel planes from the 3D plot, different planes at different heights. So then you will get a contour plot with different colors in between, where color line shows you whether the value is low or the value is high. So now let us say that this function is a non-convex function. We just assume, I will show you what is non-convex function and convex function. But for now, let us assume that this is a non-convex function. Okay. So we have started our algorithm from here. So this is the initial point given to us. So we have to go in a particular direction to reach the global optimal solution. So if we go in this direction, we will reach global optimal solution. But if we do not go to this direction, instead, if we go to this direction, then we will reach some minimum solution. but that minimum solution would not be global minimum solution. Instead, it would be a local minimum solution. Okay, then again, you can go to different directions and you can check whether you are approaching to the global optimal solution or local optimal solution. But when you have non-convex problem, it is very difficult to approach to the global optimal solution. Then this next case is if you want to maximize this objective function. The same example, let's say you want to maximize this objective function and you consider this as the starting point. So then if you go to the same direction, you will get a global maximum solution. But whereas if you do not go in this direction, instead if you go in this direction, you will end up here, because at this point, if you look at every other directions, you will find a deeper slope. So we'll not proceed and algorithm will return this one as the local maximum solution. Fine. So now we have looked into what we mean by this global optimal solution and local optimal solution. So for a non-convex problem, it is difficult to reach global optimal solution, whereas we can propose local optimal solution. But how far this local optimal solution is from the global optimal solution, that is still a concern to us. Then whenever we talk about wireless communication, so we often have optimizations problem. So this is just one fundamental example of optimization problem in wireless networks. So this example shows that you have a MIMO setup, you have a transmitter with multiple antennas, and then you have a receiver with multiple antennas. So in MIMO, when you have multiple antennas, then you can exploit spatial multiplexing. So spatial multiplexing simply means that you can have parallel links between the transmitter and between the receiver. And the number of parallel links is defined by the rank of the matrix, and or you can just directly for now consider rank to be a minimum of number of antennas at the transmitter and number of antennas at the receiver. Of course, there are many details to the rank of the matrix, but we are not going into that detail. So for this setup, what you want to do, you have the channel gain for this parallel stream, and then you have channel gain for this parallel stream. And you want to find out the capacity of this setup, and then you want to maximize this capacity by optimizing how much amount of power that we need to allocate to each of these capacity links. Sorry, each of these parallel links. So this is defined by this expression, capacity. You know how do we define capacity? Capacity is log 2 1 plus SNR. So simply you have here log 2. Since we have number of parallel branches equal to 2, you will have summation of I from 1 to R, where R is equal to 2. Then you sum up the capacity of both the links. And this you have power, then you have noise. We will not go into this. You have some channel gain lambda I, and this gamma I represents the power that we need to allocate to this parallel stream. And I will just show you later how you solve this problem. But for now, we assume that we are getting this optimal location gamma I. So how much power you want to allocate to each of the parallel links is given by this form, and this one is optimal. And if you look at this problem, this is nothing but a water filling solution, and this is very famous when we talk about wireless networks. So you have parallel branches, one parallel branch, second parallel branch, and you have some channel power gain across each of the parallel branch. Then you have a mu constant, which was defined here in the optimal solution. And then you draw a constant line mu and you allocate power to each of these parallel streams. And the stream that has the maximum lambda I will have a higher power allocated to it. And when we plot this water filling, we show that this all the lambdas, the channel power gain of each of the links, they are aligned in a decreasing order. So one with the maximum channel power gain will have a more power, and one with a lesser power gain will have a less power. So this is basically the classical example of optimization that we use in MIMO communications. Now, this slide shows to you the number of problems in optimization. So there are huge number of problems. We have mixed integer nonlinear problem, we have linear programming problem, then we have second order cone programming problem, nonlinear optimization problem. We will not go into this optimization problem, but what we need to understand is basically we have two categories of problems. So one, we have convex optimization, and then we have non-convex optimization. So when you have convex optimization problem, things are very easy. You can easily solve. There are many solvers available in the MATLAB, or there is again some solvers like CVX and AMLab. And then if you have non-convex optimization problem, then the things becomes very challenging to deal with. Now let us see some comparison of this convex optimization problem and the non-convex optimization problem. So whenever you have convex problems, you can solve this problem more reliably and efficiently. You can easily reach convergence because let's say for this curve, let's say you have a function and this is the function, okay? And then you have single variable function, f is a function of x. Let's say you started from this location. You compute the gradient, you go in the direction which has the lesser one, and finally you will converge to this location. And it doesn't matter from where you start, whether you start from this point or you start from this point or you start from this point, or whichever point you take in the plot and you start from that point, you will again reach to this globally optimal solution. So that means convergence is always ensured when we talk about convex optimization problems, and we always reach to the global optimal solution. And we have no impact of initializations because we can start from any point on this graph. We will reach the global optimal solution. And there are solvers like that help us to solve this convex optimization problem. But non-convex problem, on the other hand, we cannot directly solve these problems. We can provide some approximate solutions, or we can provide some local optimal solution. Because let us again look at this function of x. Let's say you have this plot. Now, let's say you started from this location and you try to minimize this function. So when you go in this direction, you will have this one as the minima point. If you go in this direction, you will have this as the minima point. And from the graph, you can easily compute that this is basically the global minima point. And when you start from this location, you do not reach the global optimal location. You only reach the local optimal solution. So that means initialization will have an impact on this whenever you have a function that has a non-convex nature. So the solution changes with initialization. Now, in this plot, if you consider this location as the initialization, then you compute the gradient, you will converge to global optimal solution. So basically, these non-convex problems, they have there are huge set of initialization approaches, and better initialization you have to develop to reach to the global optimal solution. And we can use MATLAB solver to solve these non-convex problems, but they will return us with the local optimal solutions. And there is no guarantee that we solve this problem and we came up with a global optimal solution. So now I know that let I assume that you know the basic difference between the convex optimization problems and the non-convex optimization problems. And what are convex optimization problems, I will show you now. And the problems which are not convex optimization problems are non-convex problems. Okay, so we are just considering two categories. One is the convex problems, another one is the non-convex problem. The problem which does not fall under the convex problems, they are non-convex problems. Okay, so what is convex optimization problem? So you have a function f naught x, you want to minimize this. You have several set of constraints, inequality constraints, and the linear constraints. So this problem is convex if this function f naught is convex when you are using minimization problem, or this function is concave when you are solving maximization problem. Okay, and whenever you deal with the constraints, so constraint takes a form like this: fi of x is less than equal to 0, and the left hand side of this inequality should be a convex function with x. Okay, so if you have a constraint like this, fi of x is less than some value, let's say another function of x, gi of x. If you have constraint like this, you can easily take gix here, and you can represent this form, the simple form of inequality. You can easily represent it in this form. Or if you don't want to represent, or if it is a very complex function, then you need to prove that the left hand side of the inequality is convex, whereas the right hand side of the inequality is concave. Okay, then we have linear constraints. If we have linear constraints, constraints, they are always considered to be convex constraints. But vice versa is not true. Convex constraints are not linear constraints, but linear, they are always convex constraints. So the convex optimization problem is the one where the constraints, they are either convex or linear constraints. And what we mean by convex constraints, we have defined it just now. And then if we have a minimizing, we are minimizing the objective, then the objective should be convex. And if we are maximizing, the objective should be concave. Now, what exactly we mean by when the function is convex and when the function is concave, or when the function is non-convex? So we need to look at what we mean by concave functions. So let's say you have a function whose plot is like this, is given by this. Then this function f always need to satisfy this inequality. So what this inequality implies is that if you consider any 2 points on this plot, and if you draw a chord joining these 2 points, and you compute the function in the range, the value of the function should always be less than this chord, the line that is connecting the chord. So whenever you have this form of function, you say that you have convex function. Okay, now if we consider some other examples, let's say you talk about x square, the plot for x square. What is the plot for x square? This is like this. Okay, so you draw a line between this one, any line, any line joining the any 2 points on this plot, you will always find that the function will always less than the chord. So then this is convex. Now let us look at exponential of x. So what is exponential of x? Again, this is this kind of function. Then you draw a line and you find out that the function is less than the chord connecting the 2 points, and we say that this is convex. This is how from the plot, from the visualization, you can say that the function is convex. And there are other ways to prove that whether the function is convex or not analytically. Okay, this is just for the basic understanding. So now let us see if we have another plot like logarithm of x. So logarithm of x is like this. This is the plot for logarithm. So if you draw a chord between any 2 points, now the function lies above the chord. So whenever this is the case, that is just opposite to what we have studied for the convex case. Whenever this kind of function appears, we call these kind of functions as concave functions. Okay, so that means if x is convex, then minus of x is always concave. So you have so now you have seen two definitions. One is the convex functions, another one is the concave functions. So whenever you have this kind of plot, you draw a chord between them and the function lies below the chord, then it is a convex function. Or you draw a function like this and you draw a chord joining any 2 point and the function value lie above the chord, then these functions are concave functions. So now let us go back to our classical example of water filling. So what do we have here? Let's look at the objective. Okay, so objective is log 2 of 1 plus, let us represent this as x. So how do you define this objective? Okay, so simply you can just take this is logarithm, you define into points, this is objective that is concave. But now here you have all the functions. And whenever problems or non-convex, sorry, whenever you are doing functions or concave functions, you have a property called non-negative sum of all concave and convex functions is also convex or concave. So that means if you take a sum of this value and this is concave, if you added this up n number of times, the resultant function will always be a concave function. And what you are doing, you are basically maximizing the concave function. So maximizing the concave function means you have a convex optimization problem here in this case. And the constraint, just look at the constraint. Constraint is summation I is equal to 1 to r, then you have gamma I equal to the total power mt. And what is this? This is linear constraints. So by looking at the definitions of convex functions and the concave functions, you have said that this problem, the capacity maximization problem, what we call the water filling problem, is basically a convex optimization problem that has concave objective function and linear constraints. Okay, so now you have some idea about this convex functions and concave functions. We will proceed towards some examples, some fundamental examples of convex and the concave functions. So exponential, we have seen exponential, plot of exponential is like this. This is convex function. Then power, if you look at the power, let's say x square, you will see the plot is like this. Okay, then if you take square root of x, if you look at the plot of square root of x, this will come out to be a concave. This is no. So you have a condition here in case of power, whenever you have x of p, and if the value of p is greater than 1 or less than 0, then in that case it is a convex function. Okay, then we have further examples like logarithm of x is a concave. This also we have seen. And then norm is always convex. Why norm is always convex? Because we can always write norm in the square root form, square root of, let's say, x minus x0 whole square. And this is the variable. So this is constant. X0 is some constant. You have a variable x. Then what is x raised to power square? This is convex. And the square root is an increasing function, and you will get norm always as a convex function. Then there are some other examples. We'll not go into that. So now you have seen that the function, when the function is concave, when the function is convex, by just looking at the plot of the function. Now, how do we prove that analytically? We need to prove that analytically because for visualization, we can get some intuitions on to prove that whether the function is convex or just look at the plots, or we can just post the plots on the research paper and show that, okay, this is convex. No, it doesn't work like that. So there we have some conditions to define whether the function is convex. So first condition is the first order conditions, and second we have second order conditions. So what this first order condition indicates us, it states that if you have a function f of y, then at every point in this function, you have to compute the tangent of this curve. So whenever you compute the tangent, if the tangent always lies below this curve, then you can say that our function is a convex function. And this you have to prove by computing this form, the derivatives form, first order derivatives. So then this basically this first order conditions, they are not basically used in the research, but we are more interested in the second order conditions because they are generally relatively they are easier to evaluate. So we basically consider the second order conditions. So let's say this f is twice differentiable. Then in that case, you can compute the Hessian of x. So whenever you computed the Hessian of x, the Hessian should be greater than or equal to 0. That means if you computed the Hessian and the Hessian is positive semi-definite, you say that the function is convex. and and when you prove that the function is convex, you don't need to prove that the function is concave, because when the function is convex, and if you take negative of convex function, it would be a concave function. Okay, so once you prove that the function is convex, then you can easily take the negative sign and you can say that the function is concave. Then also you have studied in your mathematics, like if you have a single valued function f of x, which is a function of x, you can directly compute its first derivative, then you can compute its second derivative, and from there you can comment on the convex, whether this function is convex or whether the function is non-convex. But these are some advanced when you have more number of variables, so then you rely on this Hessian matrix. So what we can do, there are some set of composition rules which state that if you have a function, let's say f is a function of h, and h is a function of g of x. So basically this g is a function of h, and this h is a function of g of x. So whenever you have this kind of function, you can use this composition rules. You can check whether your function is convex or your function is concave. So let us look at this example, how we can say that whether this is convex or whether this is concave. Now we have seen that what is x square? X square is convex. Okay, so now from these rules, let us take out where this x is convex. X is basically, this is g of x, and this is h. So g is convex, so we are into this form, or whereas g is convex here, g is convex here. Okay, so now we have seen that this is convex, so we can rely on this one, or we can rely on this one. These two, they are not an option for us. So now what is exponential? We have also seen that exponential of x is also a convex form. So when exponential of x is convex, let's see where h is convex. So this here, h is convex. But again, one thing that we need to consider into mind, that it should be a non-decreasing function. And exponential of x is a non-decreasing function. So this condition is satisfied in our case, and this condition implies that the function is convex. So without computing the derivative, by using this set of composition rules, you have proved that your function is convex. Now let us look at the other example. Okay, log of square root of x. So this square root of x is a concave. So you can just neglect all the other terms where this g is convex. So this is not in our interest, this is not in our interest. We are focusing on this case and this case. And what is logarithm? The plot for logarithm is this, and we have seen that logarithm is a concave function and is also a non-decreasing function. So where this h is concave here, and we are in this condition. And composition rules that makes our life easier. This were basically the simpler examples, but it is very helpful when you have complicated examples. From there, you can easily prove that this is convex or convex without actually computing the Hessian matrix and second order conditions. Now, it is very difficult for us to always, you have some function and then you always compute Hessian, and then you check whether the function is convex or not convex. But what I want to do, I am very lazy. I cannot for every function I can just compute Hessian to check whether it is convex or not convex. What I will do, I will only check whether this is convex once the plot of the function is looking like a convex function. Otherwise I will not take this much pain of proving that the function is convex. So now there are different ways to see whether you can check whether your function is convex or not convex. Now in the first example, if you look at this plot, so what are your opinions on this plot, whether this plot is convex or this plot is concave, by looking at this plot? If you take a line chord between these, sorry, if you take a chord between, let's say, these 2 points, then the function always lies below the chord. If you look at, let's say, you are looking at this region. If you take a function, you take a chord between the 2 points, but now in this case the function is above the chord. So that means in some portions we have convex, in some portions we have concave, but over all the domain of this x and y, it is not convex or it is not concave. So basically this is a non-convex function. So we will not prove whether this function is convex. We will not go into more details like computing the Hessian and then proving that, oh, this function is non-convex. So we just did all the mathematics just to prove that the function is non-convex. So by just looking at the graph, we can show that whether it is non-convex. At the other plot, this one, the center, middle one. Two-dimension plot, you have a function and draw a line between any 2 points, draw a chord, and you will find out that the function is always below this chord. So that means this is basically a convex, or we can say it look like for this range that we have selected 200, it look like the function is a convex function. So when it look like the function could be a convex function, then we can go on computing the Hessian to show that yes, this function is a convex function. Because why it is mandatory to prove that a function is convex using Hessian? Because there could be some range in between this 0 or 50, or there could be some small interval where the function is not convex. It is in the plot, it is appearing to be convex, but it is not actually convex. So that is why we need to also prove analytically that the function is convex over all the range. So if we look at this plot at the right hand side, you will see that this is the convex and this is the concave, and you have shown that this objective is non-convex. Then look at this plot. You take a chord and the function always lies above the chord, and you can say this is concave function. So once you have identified this convex and concave and non-convex, then you can do the proofs, or you can do many things while proposing the solutions. I will show you later on how you can use it. So now you have proved the function is convex. You know how to prove that the function is convex and how to prove that the function is concave and when the function is non-convex. So what if the function is neither convex nor it is concave? And you know the non-convex problem, in case of non-convex problem, you cannot directly solve the problem because it will lead to the local optimal solution. So now next, how to find this globally optimal solution when you have non-convex problems, or we just say that we are satisfied with the local optimal solution. But if you are not satisfied, then we need to understand how to find this global optimal solution. For simple problems, when you have limited number of variables, you can develop a way to reach to the global optimal solution. But when you have large number of variables, let's say your problem is m-dimensional variable, in that case, it is very complicated and very challenging to obtain the global optimal solution. And then you have to satisfy with the local optimal solutions. So there are different approaches that you can follow. The first one is check if the problem is pseudo-convex. So let us understand this by giving you this example. So this is the B part, is the convex. You draw a line, and the line, the function falls below the line. The function is convex. Now let us look at this plot C1. Let us draw a line between these 2 points. And the function lies above the chord. So this is not a convex function. But there is a class of this convex function called as pseudo-convex function. And these functions, these pseudo-convex functions, they are unimodal function. That means these kind of functions, they only have one global solution. They do not have local solutions. So that means if you have a function, like if you can prove that from the global optimal solution, the one side of function is decreasing or the other side of function is increasing, then you can prove that this kind of functions or pseudo-convex functions. And if you can prove that the function is a unimodal function, then also you say that the function is pseudo-convex function. And mostly all the properties of this convex function apply to the pseudo-convex functions. There are many exceptions, such as this non-negative sum property. If you take the summation over convex function, it is convex. But whereas if you take summation over function that is pseudo-convex, it is not convex. But the main thing is you reach to the global optimal solution very easily when you have pseudo-convex function. Okay, then you can prove that the problem is conditionally convex. For simple problems, let's look at this first plot. This is a non-convex function, and it has a local minima, and it also has global. So for a simple problems, you can always divide this range into two parts. Let's say we divided this range into this part. Okay, you computed the second order derivative, and then you prove that this is the range where the function is convex. Okay, then you can also select other range where the function is also convex. Okay, this is the range where the function is convex. So we have two conditions on convex functions. So we define this as a function is conditionally convex over this range x1 and this range x2. And then other ranges you can employ linear search or exhaustive search. Basically, what we mean by this linear search and exhaustive search is like, let's say you have a function that is x comma y, and you want to obtain this optimal value of x and y that has the minimum value of these functions. You just simply do one for loop for x, compute the function, you then do other for loop for y, you put end, and you compute for all the values of x ranging from anywhere to anywhere. What is the bounds on the x and what is the bound on y? You have to consider all this into account, and then you compute the function, and the whichever value of x and y has the minimum function value will be treated as optimal value. But the efficient, it is computationally expensive, and when you have many variables, this goes like variables. How do we do? Will you create n number of values to compute the function value? It will take a lot of time. With things, you can divide your function into a conditional convex function. You can say in some part the function is convex, and in the other part the function is not convex. And then you can apply the solvers, convex solvers on the region where the function is convex. In the non-convex, you can apply this exhaustive. Reduce the dimensions of the x. Compare said the X search, you select the minimum from these two, and you point is the global. This is one way of doing this problem or dealing with the non-convex problem. And the convex, then what you can do from the second derivative, from Hessian, you need to check what are the kind of variables or what are the different functions that are making function non. Then you can also 0 to make the matrix positive semi-definite, and then you can apply iterative schemes. And then if you cannot do anything like this, you cannot prove that it is conditionally convex, you cannot prove that the function is convex, you cannot identify what are the approximate to have problem, then you can always propose some heuristic solution based on from the plot, and then you can compute bounds Okay, so now we will look at some examples of how to propose some heuristic solution for the non-convex problem. Okay, so the model is like this. You have initial location from the UAV trajectory optimization. You have initial location, you have the users that are distributed over the ground, and then you have the final location. You want to design the trajectory of the UAV in going from the initial location to final location. And uh, just for your reference, I have just shown the function of this outage probability. So our objective is we want to minimize the outage probability over all users. Okay, so I have shown the objective here, the outage of phi, and then I have shown this energy that is
So there is no sound.
Hello, Nishant? Dr. Nishant? Dr. Nishant, your voice is missing.
Hello. Hello.
Yeah, please
Yeah,
go ahead.
Rohit. Are you able to see my screen?
No.
No. Then there is some problem with internet. Okay, let me quickly join the call again. Okay.
और ये ट्रेन वाली देखो आपकी स्टार्ट
Yeah, visible now.
क्योंकि स्टार्टिंग में अगर आपकी एक्यूरेसी बहुत ही जीरो से होनी चाहिए, थोड़ी सी नीचे से होनी चाहिए, तो इस पे ध्यान दो कैसे कर सकते
Your slides are visible now. Your audio is not coming.
थोड़े से बढ़ा दो उसके। देन अभी तक मुझे क्लियर नहीं हुआ है कि एक इपॉक में कितनी इटरेशन होगी। ये हमको ही पता होता है जो
Now your voice is coming and your slides are also visible.
ये प्रोग्राम
okay, then fine.
Okay.
Okay, so we have some constraints. The first one is the energy constraint. Then we have initial location to the final location constraint. Then we have height constraint, and then we have velocity constraints. Now let's look at this objective function and the constraints one by one. So what you can say about this constraint, velocity constraint? So it takes the form of Vm less than some constant c. So you need this one to be convex to have this C4 convex constraints. And velocity, we know velocity can be represented in terms of the distance, and the distance is nothing but this square root of x minus x square. So basically this convex. So then in the second part, let us look at the constraint C3. Height is greater than some constant height. So basically this is just like a bound on the Zm, so it will not impact our solution much. It will just state that our height should be greater than some threshold height. Then C2, we have a linear constraint. And then if we try to look at this constraint C1, when I plotted this function of energy, it velocity plotting this. So, okay. So now from our understanding, this is not a convex function, but we can represent this as a pseudo-convex function. Function having only one global minimum. But the concern is I am having summation of these pseudo-convex functions, which is not a convex function or a pseudo-convex function. So that means we have a constraint C1 that is non-convex, and we need to deal with the constraints. The rest all the constraints, they are fine. Now let us look at the objective function. So the objective, if you look at this function is basically convex function, but you can do some, you can assume something so that you do not have to deal with the exact function, but you just have to deal with the inner part. If you just look at the plot for 1 minus exponential of minus x, so this plot is somewhat like this one. Okay, so let's say this is x and part as x, and you want to minimize this outage probability. So minimizing this outage probability implies that minimizing this x. So when you minimize this x, the outage probability will be minimized because this plot 1 minus exponential of minus x is behaving in this particular way. So we can simplify our problem a little bit, or we can simplify our objective a little bit. Instead of considering 1 minus exponential of minus x, we can only consider this one as the objective function. Okay, still it is non-convex, but we have done something. We have done some simplification to our problem. So the problem is non-convex and the constraint is also non-convex. And now we want to prove what we can say about these problems. So when I was working on this objective function, I computed the Hessian non-convex. Then I plotted the contour plot and proved that it is non-convex. Okay, fine, this is non-convex. Function is non-convex over the region x, y, and z, but it is conditionally convex over some particular value of x, y, and z. So that means if, let's say, you have a function like this one, so there was some region where the function is convex, and there was some region where the function was non-convex. So I just tried to find out what was the region where the function is convex. And then we have something, we have reduced our computational complexity because we can use solvers to form to solve here and reach to the global optimal solution in the convex part. And whereas in the non-convex part, we can apply linear search and then we can compare the two solutions. But okay, fine. We have proved that it is conditional convex, but still constraint C1 is a concern because we are unable to prove that whether that is convex or pseudo-convex. So basically it is non-convex. So then we have to go on with some heuristic design to propose local solutions. So whenever you talk about heuristic approach, they are based on the intuition. So what intuition you can have from the problem. So let's coverage region, you want to minimize the outage. Outage is minimized over all the ground users. So we is actually a point over the space where the outage probability is minimum for all the ground users. So now we designed an approach called as X approach, and we said that the location location. And we design our heuristic as, so we consider, we said final, if we want to minimize the outage probability of the ground users, what we want to do, we want our UAV to present at this vertex location for as longer durations as possible. Then we will get a minimum outage probability. In all the other positions will be higher compared to this vertex point. Okay, so then we said in the first time slot, let's say if there is no velocity constraint and there is no constraint. So in the first time slot, to the vertex location, and at the final time slot, you jump to the final location. Okay, now we put the constraints on velocity and energy. So energy is a function of velocity. So we can restrict the velocity to save the energy. So what we are doing is, okay, so what we are doing is, we are now, when the that limited in energy, what we will do, we will take okay. So now earlier it was of the vertex, now with energy, 4 time slots, it is present at the, we will have number of paths, mono and vertex and the final location. Okay, so now if in case the UAV, if the energy is so less that the UAV can reach the vertex location, so in that case, what it will do is, we have a straight line between the initial and the final location. That is the shortest path between the initial and the final. And what we will do is, we will trace a path that is between our path that is proposed by the vertex approach and the straight flight path, if the UAV cannot reach the vertex location. So this was the heuristic that we proposed. So if you just completely look at this heuristic approach, so the only computation is computing this vertex location. So once you have computed the vertex location, then it is all geometry. Then you do not need to do anything. It is just geometrical based. And to compute this location, we have some proof that the function is conditionally convex over this region and the function is non-convex over the other region. So we simply this in the convex region, and then we used brute force or exhaustive in the non-convex region. From out of these two regions, and the minimum we call it as, it is epsilon globally optimal solution. And whenever you are solving the problem using the conditionally convex, you will always reach to the epsilon globally optimal solution. Okay, so basically this was the problem. So you have bounds on x and y, linear constraints, then you have bounds, you have linear constraints, and then you have outage expression objective that is conditionally convex, and then you have optimization variable. So this is solving the problem. The convex, this complex problem, this is the one how you can design the heuristic, and then you can give something from this result. And then we said that this approach, this heuristic approach that we proposed earlier, like vertex approach, it's a very simpler approach. We just have to compute this vertex location. And how can we compute the outage, and how can we say that our result is good by just computing only one location? Because it might be the case where at this location or this location, the outage may not be very less than the outages from other states. So we cannot comment whether this solution is good or not. So then we decided, okay, let's do something further, and let us define another heuristic that puts the location in every part. Okay, so what it is doing, let's say we have a UAV present at this location. We know what is the maximum velocity that the UAV can fly. So we can draw a curve at this location. So this is the sphere which shows that the UAV can reach to this location at the present. And again, we also want location. Let's say this time slot is M. we also want the UAV to reach the final location at minus m per times.
Hello.
We will draw another final location, stating that if the
Dr.
UAV
Nishant?
is yes.
Actually, there is a disruption in your audio. Can we do something for this? I think your
Okay,
connection
then
is a bit poor.
let me just remove this one then.
Now you are not audible. Yeah.
Now is it fine?
Yeah. Fully fine now. Your voice is clear and your screen is visible. Please go ahead.
Okay. Okay. So then we said that for m minus m time slots time Vmax, if the UAV is present between this region BM, then the UAV can reach the final location easily. So what we need to do is we need to compute the intersection region between this first sphere IM and the other sphere BM. So once we have this intersection region, we can compute the next location of the UAV within this region. And how we can compute within this region? Again, we follow the same procedure. We have shown that this function is conditionally convex. If this region fall within the convex, then we'll apply steepest descent. If this region falls between the non-convex or the convex, then we can apply linear search. So based on this, we computed a sequence of problems for all the number of time slots. So this is computationally expensive because we are computing location of the UAV at every time slot, but it is giving us better performance than what we have in the earlier case. So if you just try to look at the trajectories that are plotted by the UAV, so let's say this is the red one is the vertex approach. It is basically traveling towards the vertex location and then it is going to the final location. The sequential approach, let's say this blue line, it is first taking some height and then it is approaching to the vertex location, because this vertex location is the epsilon global optimal location, and the UAV wants to reach at this location and stay there for longer amount of time. And why it is taking some height in the beginning, and this is very intuitive, or we can say it is very obvious, because when the UAV is away from the users, it needs to have some height to achieve a line of sight connection with the ground users. And this is what we are seeing from this figure. Then we also computed some results. I will skip these results. So how do we sell this problem then? So we are designing the UAV trajectory. So we have two solutions. One solution is the low complexity solution that has moderate performance. It basically computes the vertex location and then it provides us the epsilon globally optimal location. And this is a one run greedy approach whose aim is just to reach at that vertex location. Then we computed high complexity scheme and high performance sequential approach that computes the M location in all the time slots. So what are the other things that you can do instead of proposing this heuristic approach? You can prove whether this function is convex in X individually or in Y or in Z. Then also you can reduce some computations. You can either prove the function is convex jointly in X and Y and individually in convex, or you can also prove that the function is convex jointly in Y and Z or individually in X, the other way around. And then when you have proved, if any of the cases is applicable to your scenario, then you can use alternating optimization. And if you cannot prove that the function is convex in any variable, then simply, if you do not want to propose heuristic, you do not want to do alternating optimization, you do not want to prove whether the function is convex or not, just make approximations, just use first order Taylor approximation to convexify the constraints and to convexify the functions, and then directly apply the alternating optimization algorithm. So this problem was solved without using any CVX solver or MATLAB solver. We just propose a heuristic in this case. So in the next example, I will show you how do you solve your problem with the MATLAB solver. Okay, so the setup is like this. You have initial location, final location. One UAV is going from the initial to the final. The other UAV is going from the final to the initial. And this is the problem. Out of this problem, if you just closely look at this problem, we have said that in constraint 10C, the norm is basically the convex. So norm is convex, but we have the constraint here that x convex is greater than equal to some constant. And the convex constraint, the definition of convex constraint indicates that the function should be less than equal to 0 and the function should be convex, which does not take this form. So this is not convex. Again, we have energy, pseudo-convex function. This is non-convex, so we have non-convex constraint. And then the rate function, and we have seen that rate is basically b log to 1 plus SNR. SNR is a function of locations of the UAVs, and this is not a convex function. And we want to maximize the minimum of all the rate among the users. So this is kind of a fairness problem. We want to maximize the rate of the minimum users, and we want to optimize the bandwidth and the trajectory of the UAV. So the very first problem that we are facing is that we have max-min function. So we'll try to convert this max-min problem into a maximization problem. This is just a simple step to convert max-min problem to a maximization problem, and there are several literatures available. You can go through the literature. This is nothing new or nothing very complex. So you just take this Rk, this has to be greater than some constant value R, and then you want to maximize this R value. And in this problem, I was very lazy. I didn't want to prove anything. And then I decided to follow this alternating optimization. I divided the problem into two parts. First, we optimize B, bandwidth, and then we optimize trajectory optimization. And this bandwidth, if you look at this bandwidth, I will show you later. If you look at this bandwidth optimization, this is a linear optimization problem, and we can use MATLAB solver to solve this problem. And this trajectory optimization problem, I further decompose this problem into the horizontal and the vertical constraint to have a much simpler expressions, and then we can use alternating optimization. So this is the rate expression, and this expression is non-convex because of this expectation in between this SNR value. So now we need to make this function convex. So the idea is to introduce a slack variables. So these are the variables, slack variables, that replaces this function with some variable. So in this case, this is the expectation of the expression for the expectation of h, and we use this slack variable alpha k comma n. And if we replace this alpha k comma n in this expression, rate expression, what you will see that rate is nothing but bkm. Bkm is constant because we are dealing with the trajectory optimization problem. Bandwidth is not a variable in that problem. Then we have log. Log is a concave function. We have seen log is a concave function, and we have only a single variable alpha. So that means our objective is now a concave function. But in this process, we have added another non-convex constraint defined by alpha km less than equal to this value. And to prove this to be convex constraint, this alpha, we have no concern over this alpha, but the right-hand side should be a concave function. Then we again look into this form, which is the one that is making this non-convex. We replace that with the slack variable, and then we again add a non-convex constraint, and we repeat this process until we find a very simpler expression at the end, which is non-convex, and to that we apply first order Taylor series approximation.
Are your slide moving? Can you please check?
This slide?
You are at slide number 22, na?
I am at slide number 28.
Oh. Okay. So
the whole time you have opened the slide number 22 in the entire discussion.
after you change your audio position, na? After you change as I told you to change your audio position, after that you were stuck to slide number 22. Just give a brief summary of what happens after 2020 after this 22-23 slide.
Which slide you are able to see now?
Right now it is 25.
Right now it is 25. Okay. So the quick summary is in this is another heuristic approach. You simply compute the intersection region and then you select this region as the non-convex or the convex region. You find out the local solution by using the previous approach only, conditional convex. And then I showed you the trajectory results for this one. It is taking some height. This is because when the UAV is away from the circular region, it needs to establish line of sight connections with the ground users, and that is why it is obtaining some height in the initial phase of the trajectory. And then I showed you how I solved this problem. Two forms. One is the low complexity solution, which has moderate performance. And in the vertex approach, we only compute a single location vertex, and then we utilize greedy approach to reach that vertex location as early as possible. And then we have high complexity, high performance, sequential approach. We compute the location of the UAV at every time slot. Then I said that if you cannot do this heuristic approach, you cannot propose heuristic approach, then you can use something called as alternating optimization, or you can also use first order Taylor approximation to make this function convex, and then you solve it iteratively. So that I will show you how to solve this problem with MATLAB. Okay, so you have the problem like this, max-min problem. You have a rate objective function, and then I showed you this 10C, 10D, and 10E. They all are non-convex constraints and to a maximization problem. So this is simple steps. You take the Rk to be greater than some constant R, and then you try to maximize this R. And then I said, I'm not proposing any heuristic in this problem. I'm just dividing the problem into two parts. First is the bandwidth as a variable, and the second one is trajectory as a variable. All this RKM is basically non-convex because of this expectation over this H matrix. And this H is given by this expression, and I want to make this function as a convex function. So what I will do, I will introduce something called slack variables that will replace this expectation with a new variable alpha k comma n. But it will add another non-convex constraint to our problem. And this constraint is a problem because the right-hand side of this expression is not a concave function, it is a non-convex function. So what we will do again, we will again find out which is the variable that is making this function non-convex. We will replace that variable with the slack variable, and then we will repeat the process, and this process is repeated till the end. We have a very similar expression on which we can apply first order Taylor approximation. And this will make our problem convex optimization. So then the solution is you fix the trajectory of the UAV, optimize the bandwidth, then you fix the bandwidth, then you optimize the trajectory, and this process repeats and between the two consecutive iterations is lower than some threshold value. So now I will show you how to solve this problem in a MATLAB solver. You have a maximization problem, you have this R, and the variable is, you have a constraint, Rk is greater than R. So So let us go back to RK. If you take this BKM is a variable here in this case, and RKM is basically a linear function of this BKM. And if you add this RKN, then also it will remain the function only. This is a linear constraint, and this constraint is also a linear constraint. And bandwidth constraint is also a linear constraint. So we have a linear optimization problem where there is no constraints. So there is a function called fmincon in MATLAB that minimizes the objective function. But we have a maximization problem. So we will just do the negative of this R. So if we just R, then in that case we are minimizing minus maximum of R. Then we define the fmincon, which algorithm it has to use. It will use interior thirds, the number of function evaluations or the number of iterations. This file, then you have constraint, they are defined in this file, and we have this A, B, A equal and B equal, they are basically the bounds and the linear constraints. Then we have is the lowest value that it can obtain is basically 0, and we do not pose any constraint on the upper value because it is already constrained by this third constraint, which is B. So this is the expression of the rate, one that I have written. So all the constraints, they are written in less than equal to form. So you just, this R is basically an optimization variable here, and this is embedded at the end of the vector B. So you have this first constraint, and similarly you have this second constraint that the rate of this user should be greater than this threshold, and the threshold in this case is 0.2, and this is the rate for first user and addition to the rate of second user. Then you have a bandwidth constraint. Again, we have a for loop and we have sum over all the bandwidths, and this should be less than 20. So you have defined all the constraints in this file, constraint 1, constraint 2, and then you have constraint 3. And 1 and 2, they are inequality constraints. So we will define a matrix here or a vector C, that constraint on the objective, and then we have individual rate constraint, and then we have C equivalent, which defines the equality constraint. So we have one equality constraint defined by bandwidth CONS, and we will define it here. And what is objective? Objective is simply a variable. We simply have a single value that is embedded at the end of the optimization vector. And since we are doing maximization, we will take negative of this X here. So then you will try to solve this problem. You will have a solution to this problem. This is how you solve your problem in MATLAB solver. You define a function file, which takes the function in this form, and then you define a constraint form that takes the inequality and the equality constraint in this form. And this is not only valid for linear programming problem, you can also solve non-convex problems with this format or with this syntax, but in the end you will get a local optimal solution. Whereas in case of convex optimization problems, you will get a global optimal solution. So the same code is valid for many kinds of problems. So in summary, we have seen what are the convex problems, how to prove that a function is convex, how to deal with when you have non-convex functions and non-convex problems. You can provide some heuristic approach, or you can use some MATLAB solvers, you can use some approximations, and then you can use Taylor series approximations. So there are many things you can use. So with this, I hope that you will have some idea on how to solve the optimization problems. Yeah, that's all from my side.
Yeah, thank you, Dr. Nishant. So the session is open for any query. If you have any query, you can open your mic and you can ask, or you can also put your queries on the chat box. Any query?
I can share with you the codes for this solution.
Yeah.
If you need any code, you can just directly email me with the code and I will send you the code for this. You can try it out.
Hopefully we have taken the recording of this section. So this session can be available live for you to work on. Also, if you need any help, you can directly mail Dr. Nishant. He will help you. Can you just share your contact information? Okay, it is here. Also, you can also share your channel information where you put some innovative videos of wireless learning.
Okay, you can directly go to YouTube and then search their wireless visionaries. You will get a channel.
Yeah, you can open
here.
By
me and my colleague.
You can open that window here, and meanwhile we can have a session, question session here. If you have any query, any question, you can put here in, or you can put your queries in the chat box itself. Okay, so we have one message in the chat box that very nice session by Dr. Nishant. Recording and PPTs will be helpful. Yeah, we will provide you with this. So I'll check whether my team has recorded this session. So if the recording is available, I will surely give it to you. And for sure, we are giving you codes for this. Presentation and codes will be available to you.
And this is my page. Please do like, subscribe, and go on. Check on what other videos are there.
You can check by your own. Before liking or subscribing, you can also check all these videos. I have also gone through these videos, and these all are innovative and easy to understand, I must say. Next message in the chat box we are having. Yes, very inspiring session. Thanks a lot, Dr. Nishant. This is from Mohammed Hamza.
Thank you.
So if we do not have any further message or further query, I think we can conclude this session. So thank you again, Dr. Nishant, for your this wonderful and interactive, informative, and this innovative session. Yeah, this is I must different way of learning from your side, how you present these things. So thank you again. Thank you very much for accepting my request.
Thank you, Dr. Rohit, for your efforts and carefully listening to my talk. And I apologize for the disruption in between. I don't know what was happening at my side. So I apologize. I really apologize for that. And if you need anything, you can just directly email me. And if you need code for this, you can email me the request for the code. I will share with you the codes for this one, for both the problems.
So with this, we conclude this session. So let's see. We have a special session on request where I will represent some of the innovative technologies in wireless communication, including NOMA and other techniques. Tomorrow, 11 a.m. in the morning. So this is one additional session from my side, and based on your request. So tomorrow we have two sessions. First one is mine, a small session for discussing NOMA and other techniques. And in the evening at 2 p.m. a special guest, Wonjae Shin from Korea National University. He is also a pioneer in wireless communication. So feel free to ask any question and get it interactive session and have an interactive session with Wonjae Shin. He is very innovative and also a pioneer in the field of wireless communication technologies. So let's connect with with you tomorrow. Meanwhile, if you have any query, anything, any way we could help you, please contact us, connect to us. Thank you very much.